So it's probably quite unusual for me to do 3 episodes in a row with the same person, but I think that this topic that he's tackling is very important, given that lots of companies and countries are behind this whole climate change. So Kevin's very keen, and he's prepared some slides today, and he's going to go into the science in depth, so that will give you a basis to make your own informed decisions regarding this. So without further ado, here is Kevin Kirchman. Hello and welcome to the Nikos show. Today on the show again, third time in a row, Kevin Kirchman.
Yes, good morning, Nikos. Okay, today I want to talk about the science. Again, we're trying to restore integrity to climate science. So I think that we all, or most everyone, study science beginning in middle school and high school, and then often in university, and then there are technical people out there. But I think people in general lack confidence in their ability to understand scientific issues. And this is a bad thing because it means we're dependent upon other people's opinions, and we have to form our own. And think about concept of democracy or widespread distribution of influence and authority. You basically have to be able to think for yourself if that model or idea is going to work. And education is supposed to provide you that capacity to think for yourself, to think independently, to decide for yourself whether something makes sense or not. And so when we all have so much of our lives in schooling, 12 years plus the 4 plus maybe another 2 or 4, that's a lot of years. We should all be very confident intellectually. That we're not raises another issue, but we won't go there now. So without further ado, let's just move forward here, and I want to jump into the science challenging the greenhouse gas theory. Okay, so basically from an overview, I've maintained the premise that someone's trying to hoodwink us with this greenhouse gas theory. Okay, so that's kind of a conclusion before I've done the explanation. You'll bear with that. But we just want to be aware what kind of opposition there is to a widespread understanding of the climate science challenge, or in the greenhouse gas theory errors. Okay, so when we talk about, and this is a bit of a review, when we talk about the air and temperatures, it's really about thermal energy storage. Okay, so this is thermal energy. Okay, that's about the temperature of the air. Okay, and how much energy it's storing. Okay, because that's what that's what temperature is. Okay, so basically we're going to go right in. So I'll talk about the screen a little bit later. I'll come back to it. But for now, I want to go. This will be the most complicated slide I'll show today. I think
reminds me of like second year physics, this like thermodynamics and Boltzmann's constants.
I hear you, but I want to this example, kinetic theory analysis. We get PV equals NMV square, this velocity and pressure and volume, the ideal gas law and temperature, the relationship. That's high school physics. Ideal gas law. PV is this middle one here. PV equals N Boltzmann's constant times T. So the relationship for most gases is dependent upon the pressure and volume is constant with respect to the temperature. Okay, so that's really important. And so there's basically the kinetic theory of gas is a mainstream theory. Gas, and it holds for ideal gases, which I'll discuss that momentarily. Gases heat primarily by increasing their velocities, not their vibrations around. And so that's really important. When we talk about the greenhouse gas theory, it's about this few amount of gases, namely CO₂, is a big discussion issue, which is 4/100ths of 1%, a tiny bit of the atmospheric concentration. And the idea is that this little tiny amount of gas is the primary vehicle through which thermal energy is stored, and changing its concentration is going to affect the total thermal energy stored in the atmosphere. Okay, so that doesn't make a lot of sense, to be frank. So again, thermal energy is what we're asking about, and temperature is what we're asking about. So back to this kinetic theory analysis, which they've seen this in high school. This PV equals nRT, or KB is T. It's the same idea. This is normally presented as R, but we wanted to have it explicit for another reason here today. Okay, so this basically says the temperature we basically take these equations, and then we substitute for PV, so we get the velocity number here, and then we basically take the PV, the ideal gas law. So we get these two relations of pressure times volume of a gas. Okay, so we're talking about the air right now. That's the gas we're discussing. And the air again is about 99% oxygen and nitrogen. Okay, so that's what we're talking about. All right, so now we put these two together, and then we come up with T equals mass times the velocity square over this average velocity of the molecules in the air, or in some container, or in this case is a general case for behavior in the atmosphere. So the temperature is dependent upon the mass of the air times the average velocity of the molecules in a constant way. That's all. Now in that equation, there is no room for carbon dioxide. It doesn't matter if it's carbon dioxide or oxygen or nitrogen or the so I'm going to skip the next page here.
For people that are not used to science, so basically when you say a constant like Boltzmann's constant, a constant is like a property of nature that doesn't change. So for example, the speed of light, that's a constant. The gravity of
it's
the
one
Earth
of the seven physical constants that pretty much define the universe, or put limits on or correspond to the world or the universe. Okay, so the Boltzmann constant is one of them, and so this is like exactly what you're saying. It's like the speed of light. But basically. This velocity of the molecules, an average velocity of the molecules, all we're saying is that the temperature of a gas depends upon how fast these molecules are traveling and their mass. Okay, that's all it is, and it's just saying that 3 kb, 3 Boltzmann constant is just the constant, whatever that number is. Doesn't matter. It does matter, but we're not going to go into the calculations. All we're trying to do is get a qualitative and quantitative comprehension of where we get our temperature. So we're saying temperatures are rising, then we're only saying that either the mass of the air is rising, or the velocity of the average velocity of the molecules is rising. Okay. Yeah. So where's the CO₂? Okay. So now I'm going to skip down to this. All this is pointing out is, okay, this is the above equations, the last equations, they hold for ideal gases. Okay, so how much can we assume? These are the questions we should be asking as societies and as people. We should say, hey, Kevin, so you're saying the temperature of the air only depends upon the velocity of the average velocity of all the molecules? And their mass. So we know the mass of argon and the mass of oxygen is not going to change. That's their atomic number. That's right. That has nothing to do with those aren't going to change. So the only thing left is a velocity there. So why are these things? Are they going faster? Okay, because does CO₂ make them go faster? And okay, so basically this says many gases such as nitrogen, oxygen, hydrogen, noble gases, argon, and helium. Okay, so argon is 1% of the atmosphere. Nitrogen is 78, and oxygen is 22. Okay, so these are all many gases. Some have and some heavier gases like carbon dioxide and mixtures that can be treated as ideal gases within reasonable tolerance, about less than 1% over a considerable parameter range around the standard temperature and pressure. And I say in the troposphere, which contains 80% of the mass of the atmosphere. Okay, so I'll explain this a little bit as a long sentence. But basically, in the troposphere is the first 12 kilometers of the air of our atmosphere, and it's about that's where 80% of the mass is. So when we're to talk about that space, we're basically saying that all the mixture air and all these basically components of it, argon, nitrogen, and oxygen, which make up 99%, include and that little tiny bit of carbon dioxide, they can all be treated as ideal gases. Okay, so that means
What an ideal
water
gas
vapor
is.
What's that?
I've forgotten what an ideal gas is.
Yeah, what were we saying? Yeah, well, it's important. Actually, when we're talking about climate science, this science isn't going to get much farther than this. We're going to stick with this today and understand this, so we see how simple it is. So it says simple, and it may at first when you confront it with a bunch of formulas, everybody goes, "Oh no!"
The ideal gas law is PV. Yeah, okay, I forgot you. I remember.
Yeah, NRT basically, but it's the same thing. And R here normally is a number of molecules times Boltzmann's constant, but that's the R. P equals nRT, and so that's the normal one everybody knows. Okay, and then then you're basically this other one, the average velocity. Okay, so this is the kinetic theory of a gas. Okay, so this is mainstream physics. All it does, and with my manipulation of the equation, I just wanted to show that temperature, according to kinetic theory analysis, for an ideal gas law, which is what the air is, at least for most of the troposphere, it's behaving in an ideal gas law. The temperature is dependent upon the mass of the air and the velocity and the average velocity of the molecules. That's it. It doesn't matter which molecules. CO₂ even. It's just the velocity of CO₂. There's no atomic number in there, and the mass of the air, okay, is of these molecules. Basically, these things are temperature only is depending upon on the speed of the molecules, okay, because given the same air. Okay, so that's
the people that promote global warming would say that the CO₂ increases their velocity with the energy absorbed. So that's how they get around that.
This shows that the temperature is not dependent upon the molecular weight or the triatomic nature of those molecules. They can argue that, but this says, wait a minute, that's not so. You can't argue with me about CO₂. That has nothing to do with it. CO₂ is operating as an ideal gas. So you can't use that argument. I'm sorry. It's kinetic theory. This is an ideal gas for the troposphere. There's no space in here for molecular vibrations. And I know, so we talk about molecular vibrations, and
yeah, it's different. Yeah.
But that's not for ideal gases. We don't worry about that. Ideal gases, we're only concerned about their velocity. And so I don't want to hear any rubbish about CO₂ or anything else. CO₂ is behaving like an ideal gas too. And then I'm going to explain that a little bit more, because this gets kind of interesting here. So basically, mainstream kinetic theory of gases for ideal gases says there is no global warming because of an increase in CO₂. Where is that in this equation? It's not there. It is nothing. There's no, you'd say, oh, but with the CO₂ went from 0.03 to 0.04. That isn't in there. So, it is in there, but it's only 0.01%. And we were talking about the average velocity of the molecules and the mass. This mass the mass change of that is negligible. And so you don't even, there's no impact. This is what's guiding the temperature of the atmosphere, not CO₂'s vibration states. So okay. Now I'm going to go to skip down here too. Okay, boom. Okay, so this is interesting. Okay. This is about the Cp is a specific heat constant. This is about thermal energy again. The specific heat constant means how much energy it takes to change 1 gram or kilogram or whatever of a substance. Okay, so how much how much energy, how much kilojoules, how much energy it takes to change a mass of a substance by 1 degree Kelvin or whatever. It doesn't matter. Temperature could be Celsius or Kelvin. Okay, so it's because they're both the same in the absolute or the abstract sense. Okay, so basically this graph says, okay, so this is really interesting. This black line here is the amount of energy it takes to change a mass of CO₂ by 1 degree, basically. Okay, so this it's just a measure of the amount of heat that it requires in order to change the temperature of the gas. So when this CO₂, this black line, is when the pressure is 7.6 millipascals. Now, 1 atmosphere is 0.1 millipascals. Okay, so that's a 1 atmosphere to give it. So when the atmosphere pressure, or when is 75 atmospheres, which is like Jupiter, then CO₂ then we start to see that special case of triatomic moleculism that the global warming promoters they're worried about this little spike. They're saying that what's happening here is that the molecules of CO₂ are able to store, or is two ways to look at specific heat. One is that it's the amount of energy it takes to change the temperature, and the other way is to look at it as the amount of energy that's stored at that temperature. Okay, so there's 2 ways of looking at it. So here at 76 atmospheres, you're darn right, it matters, but only in a specific temperature region, which is reasonable. This is around standard temperature, but it only matters at a super high pressure. So that has no relevance on Earth. Okay, maybe below the, maybe 100 miles below the Earth or something. I don't know, so or be below the surface of the Earth, but it doesn't have any relevance to our atmosphere. There's no 76 atmosphere place in the air. Okay, that's we go from 1 atmosphere on the ground to less above it to space. So there's no 76 atmospheres. So
that basically that if it's at 7.6, then it's saying that to go from 32 degrees to 33, it takes a lot of energy.
Yes, exactly. It does, and here's why. It takes, because it's changing the vibrations, or this is where the degrees of freedom of the molecule matter. What I'm saying is the translational velocity of the previous slides. Okay, that's the X, Y, and Z degrees of freedom of molecules. That matters. You see, that's the whole point of the kinetic theory analysis. That's the only thing that matters, not the energy states or the state of the electrons or how they're vibrating with respect to each other of the atoms. See, CO₂ has 3 atoms. Nitrogen is N2, and oxygen is O2 generally, and predominantly in the atmosphere. So they have 2 atoms, and CO₂ has 3, and that 3 atoms means there's 3 ways that there's more ways this thing can vibrate and move, that can store energy. So when we look at an N2 and O2, they can move, the two atoms can move back and forth with respect to other, but that's about it. But when you get 3, you get other kind of harmonic arrangements. And so the global warming crowd has been saying that those harmonic arrangements, those other degrees of vibration, allow CO₂ to store more energy. Okay, but this graph says no. That's only when at the pressure of 76 atmospheres.
Right, I got you.
So then it matters, yes, but that's Jupiter, not on Earth.
Because that basically says that this CO₂ is absorbing sun energy all through the day at 7.6, and then it's maybe not emitting it as fast as it was if it was at a lower temperature.
Yeah, but I want to go now to this blue line. The blue line is the Earth line. Okay, see the blue line down here at the bottom?
Yeah.
It's basically flat. That doesn't tell me any. That only says that it doesn't make any difference. Okay, so the black line is when you're on Jupiter at 76 atmospheres. Okay, that's a huge amount of air, because 76 times what we have at the high pressure in the air on the surface of the Earth. Okay, so the black line is Jupiter. The blue line down here is Earth. So you don't see that spike on Earth. That has nothing to do with us. That's the vibration of the CO2 atoms. That's where it is. That's where it needs more energy to change its temperature, or it stores more thermal energy, but only at 76 atmospheres, not down here on Earth. On down here on Earth, it's flat. I don't care. It's so now here's this is the okay. This little bit here between the blue line and the graph is shown over here on the right as an amplification. Okay, so basically, you see, so I've put this, here's the temperature, and here's Earth's conditions here, basically. And you see this CP, this is the specific heat, okay, which is, even in high school, you were taught about specific heat. It's the amount of energy that takes, for example, it takes to change the degree of or a gram of water 1 degree. Okay, that's a specific heat. So we're talking about something that you all have seen before, even though you don't maybe remember it 20 years after, 10 years or whatever after high school. But so the specific energy of CO2 is less than air, okay, in Earth's conditions down here in the troposphere. Okay,
that's so crazy.
It means that CO2 is less of a greenhouse gas than the rest of the air. Okay, so the guys, when William Happer, okay, he's a professor emeritus at Princeton, Einstein's university, gets on there and starts and endorses the greenhouse gas theory, and although has some quibbles with some nuances, he's flat wrong. Okay, it doesn't, CO2 is less of a greenhouse gas than the rest of the air, than the nitrogen, the argon, and the oxygen that make up most of the air. It is less. So here's Earth's conditions. Okay, yes, it does matter on Jupiter, but it has nothing to do with where we live on planet Earth. Okay, so
climate change matters, like I said, on Jupiter.
Yes. Exactly. So, if we lived on Jupiter and everybody was worried about carbon dioxide increasing in the atmosphere, I say we have a concern on Jupiter.
But I mean, it's only a very small, even on Jupiter, if you're worried about global warming, it's only a very tiny fraction of the degree scale. Then it's fine. So
that's right. It's only right. There's only one at one temperature. Now the temperature of Jupiter is probably way down here, is 0. So even this, when I say it only matters on Jupiter, it definitely has the pressure, but the temperature, well, that's another issue, because I guess Jupiter is just a big gas planet. So the farther you go down into the atmosphere, the higher the pressure goes, and it will get hot down there, I imagine, too. I don't really know, but nonetheless, I don't want to know.
I mean, we should send a radio message to Jupiter, tell them just to be careful when they get to 32 degrees, that they don't mess up the atmosphere somehow.
Yeah, but this graph shows us, and this understanding explains to us that CO2 has absolutely nothing to do with thermal energy storage on the planet Earth, where we live. So any of the scientists, they're pretty much looking like Marxist academics who are biased in their science. And in the biasing and the general biasing it's the corruption of science, the destruction of science for political motives. Just the concept of destroying science and destroying the integrity of science and the rule of data over theory, this is of such a great threat to human welfare that it's just incomprehensible that so many people would be on the take. But that's the world we live in. Okay, not this one. Okay, so
I mean, we put out to the scientists on LinkedIn, the climate change scientists, to come and debate you on this kind of stuff. So the invitation's still there, but
they don't want to respond. They haven't. Nobody has, and we get a lot of people agree with me, but nobody's disagreeing, and so they don't. I mean, technically, there's a game you play when you're a kid called King of the Hill, right? When you have a little pile of sand or something from a construction site, and you got to stand on the top of the hill and push everyone off, and well, so far I'm still king of the hill here. And so in terms of a theory, if nobody's, you can say, oh, we don't want to debate you because whatever reason they want to say, oh, but you're not a specialist and
you're not worth our time.
Yeah, well, it's rubbish. They're wrong, and I have a lot of climate scientists, PhDs in atmospheric science, PhD in physics that endorse what I've said, that have agreed and said, hey, Kevin's right. He's showing this CO2 has nothing to do with anything. And there are other perspectives, but this was my work here, discovering all these things by asking all the questions, by asking about. This back to this kinetic theory analysis, this is really important. Temperature depends only on the average velocity of the molecules, and independent of the nature of those molecules, excluding the mass, which is that's just saying that that doesn't have anything to do with anything really, because the masses of the molecules are relatively the same anyways. So they're on a magnitude level basis. So the temperature does not depend upon vibrations. Okay, so that's their whole global warming theory. That it depends upon the vibrations. That's wrong. It's only dependent on the velocity. Not the vibrations, the velocity, the translational velocity. That's what that says. Okay, so that's a really important thing. And again, this is for ideal gases, which is the troposphere. 80% of the mass of the atmosphere is operating within less than 1% of error as ideal gases. Okay, now water vapor is a special case because of steam, et cetera. But even water vapor is not, and again, it varies, but it's on the order of 1% of the atmosphere. So it's still a tiny bit, and then you only have to. You might find something that it's not contributing to global warming either. In fact, I say water vapor cools the Earth. Okay, so water vapor, everybody says, well, that kind of makes sense. If you've got water all over the ground, it's cooler because it's evaporating and it's absorbing thermal energy as it evaporates, and it's cooling the temperature.
So when water absorbs, what is it absorbing from the heat? Is it absorbing the light energy, or what is it taking out of the atmosphere?
Yeah, think about energy as energy is all sort of the same. Electromagnetic energy, whether it's light, heat, it's all EM, electromagnetic energy. So just sort of look at it like that. I mean, there's light, there's infrared, there's ultraviolet, there's thermal energy, ranges, et cetera, but it's all the same. Photons, okay? Photons are how energy is transmitted, unless it's just because molecules are bumping up against each other. Okay, so again, water vapor, you can't really approximate it as an ideal gas. There are some caveats, but it's less than 1% generally. But I would say water vapor cools the Earth. It absorbs thermal energy, okay, when it's evaporating, because it's a change of phase. It's going from liquid to gas. And when it gets evaporated, that takes thermal energy out of the air and stores it in the phase change. Okay, so that cools things. That's evaporative cooling. Okay, so water vapor in clouds reflects sunlight. Okay, so reflecting the sunlight, it doesn't come down to the Earth. It doesn't heat the atmosphere. It just bounces back out to space. So we know that water vapor as ice on the poles reflects solar energy. Water on the ocean absorbs, but it also reflects quite a lot of energy. But it does absorb solar energy, but that's not in the air. Okay, so that's just water in the sea. Water vapor is a cooling friend. A desert doesn't have water and it's hot. where in the same latitude, a desert is with water is a forest, and a forest is cooler than a desert. And water allows photosynthesis, which is storage of thermal energy and carbon life, okay, and the basis of all life on Earth. So water vapor, to me, is not a store of, I mean, it is a store of thermal energy, true, but it's less, it's on the order of 1% of the atmosphere, and it varies. But it generally cools the atmosphere. It does store thermal energy. I can go back to, let me see if I got this one. I don't have that other. Oh, no, I have. Here it is. Okay, so yeah, I said I was going to come back to this. Okay, so again, it's about thermal energy storage. Okay, so water vapor here, again, we talked about, this is, again, a CP number, this specific heat. How much energy does it take to change 1 gram of a substance 1 degree? Okay, so remember, CO₂, this is the CP on Earth, okay, not on Jupiter. On Jupiter, this would be, goes crazy. It goes up here to, look at that. It goes to 118 or something like that, right? Okay, so on Jupiter, it matters. This would be 118, and I'd say, oh, here we are in Jupiter. We've got to get rid of our CO₂, because it makes a big difference. But not in the troposphere, the constant pressure, CO₂ stores less thermal energy than the air in general, certainly less and also less than the nitrogen, less than oxygen. Water vapor stores more thermal energy, but it's 1% of the atmosphere. Okay, so yeah, but then these clouds that you see in the background, they're reflecting solar energy. So I wouldn't, is it a greenhouse gas? No, I would say, no. I would say the primary greenhouse gases are N2 and O2 because they're 99% of the atmosphere. They're the ones storing all the thermal energy. And I'll discuss this late in a forthcoming book. But basically, all the energy that we have in a daytime in the atmosphere is going to be radiated into space by the morning. Or not all of it, but most of it. That's when it gets the coolest in the day, is in the morning, because the air has been radiating all night long. By morning time, the temperature's dropped. Then the sun comes out and starts to warm it again. There's very little greenhouse on the Earth. Okay, we don't have a plastic cover to hold the air to keep it from mixing. And it doesn't stay, it stays here by gravity, but the energy that it holds radiates overnight. And if the sun doesn't come up tomorrow, if the sun sort of just got zapped up by a black hole, a passing black hole or something, then we would freeze to death in days. Okay, so maybe we get away with a week, some of us, or 2 weeks, but we're in trouble. So because there's not enough greenhouse to be talking about. So now, okay, so let's just say that you live in Los Angeles. A lot of people have been to Los Angeles. It's a big sprawled out city, and there's concrete everywhere and rooftops, black rooftops, cars driving around, air conditioning running, burning fuel and turning the fuel into heat. Okay, and the electricity, is all driving motors, which then become heat. Okay, so heat. So all day long, they're driving around and running motors and air conditioners and breathing in and out and warming the earth. And then when the sun goes down, then it all goes to the space, into outer space. And that's the world that we live in. So if Los Angeles is warmer than it was 100 years ago, okay, it's because it heats up more in the daytime. And because of all the people moving around and driving and using fuel. Okay, but
if they wanted to cool, do you think the air conditioners in cars actually contribute that much to the heat of the town?
Guaranteed, and also the roads and the concrete and the roofs, that guaranteed. That's what warms the earth. Okay, if that's the anthropogenic warming. Is the burning of fuel, the roofs, the black, the turning of it's when you take away your trees convert thermal energy into carbon life. Okay, so they're good. Okay, asphalt is a tar, comes from the soil or comes from under the earth, but basically, and it's a hydrocarbon as well, but basically as a black color, it absorbs thermal energy and warms the surrounding air for a little while until the night comes and it all flows away. So if they want Los Angeles to get cooler, because maybe let's just say in the last 100 years the temperature has increased 5 degrees, which is, this is just a guess, but it's probably on the order. Okay, so if they would like to get rid of the 5 degrees and go back to the way it was 100 years ago, then they should shut off their air conditioners for a day,
Yeah, totally.
and see if it works. I don't know if that's important to them. Either that or move away to a place where it's cooler, right?
I just read something on BizFluence today. It's I think the founder was talking about this conference on climate change, but the airport was like jam packed with like Gulfstream private jets and all this kind of stuff. So
yeah,
interesting, right?
It's rubbish. The air. I mean, there is no global warming other than the warming that we warm the earth with every day. And when night comes, it gets cooler everywhere. With occasional exceptions. Maybe Las Vegas warmer at night, because so many lights or something. There's people driving around. But most places it gets cooler at night. Okay, and that's it. There's no. If we as a planet are afraid of 1 degree increase in temperature, give it 30 minutes. That's the title of my next book. If we want to cool the earth by 1 degree, give it 30 minutes and it'll cool down. In a solar eclipse, we see the earth, or we see the temperature under a solar eclipse path. We see it drop 5 to 25 degrees in 30 minutes. So that's how there's an example of your greenhouse. It's not much of one. Yes, it does matter. The atmosphere provides us the breathing air and the CO₂ to build our carbon life form. And so that CO₂ is really important. It's a tiny, tiny amount. You can see there, 0.04%. Wish we, the more we have, the better off everyone is, because the more things grow and the more productive our agriculture is. So pretty much it's a good thing. But it doesn't matter how many people say the emperor has has clothes, because that's where this CO₂ is today's emperor. CO₂ says, thou shalt stop using me or stop producing me. It's the emperor. It's a dictatorship of CO₂. But that emperor has no clothes, even though everybody keeps saying he does. And that's humanity. Like I say, sadly, we can take an idea and treat it as if it were the world itself. And that's one of our failings as a species. We have great capacity to create and modify and challenge and innovate ideas, but those ideas always have to be respected for their nature as human inventions, right? And so basically, so that's the idea here I wanted to communicate today. It's not all the science in the paper that we can give you a reference to, listeners, but it's a pretty important idea. And just to summarize, it's the kinetic theory, which is a straightforward understand that you learned in high school, applies to an ideal gas, which is the nature of the gases in the troposphere. They're operating an ideal gas. It says, hey, if you manipulate around temperature, only depends upon mass of the air and the average velocity of the molecules. So this is important for a further explanation when I say that, but that this velocity is affected by photons. Okay, so that matters. And the temperature heats when the sun heats the air. Okay, so when the sun heats the air, the temperature increases. Yeah, duh. Okay, so temperature is velocity increases. Okay, so that's so this is science. There's some equations. They're just not that tough. Most people with a high school education have seen this PV equals nRT. Okay, and there it is. Okay. And so this is, so yeah, it's science. Okay. But you guys, everybody has already seen this stuff before. You're supposed to know it already. When somebody comes to you and tells you there's global warming, you say, well, but the temperature of the air only depends upon the velocity of the molecules in the for ideal gases, which is what the gases are in the troposphere. They can talk to you all day long if there were uranium floating around in the
They'd probably
air,
be
which
shocked if
has
you
a high
replied back
molecular
like
weight.
like that. Ideal gases in the troposphere.
Yeah, well, they wouldn't know what to say. What are they going to start arguing about against the kinetic theory? I mean, of gases. That's what they have to do in order to defend the greenhouse gas theory. They're going to have to show the kinetic theory of gases is wrong, and that ideal gases don't exist, or something. I don't know what they're going to do, but they're kind of screwed with the greenhouse gas theory. It's a bad theory. It's an invalid theory scientifically. And so I've got one other slide here and then I want to cover something that we mentioned last time we talked. So basically, this is about as a CO2 molecule picture. Okay, so it can only radiate a limited amount of energy. So this is under the assumption that the photons come in here. And they're specially absorbing that infrared radiation. Okay, this is the greenhouse gas theory. Under the assumption that this greenhouse gas theory is valid, which it's just not. We just showed that. Under the assumption that it is valid, so here's a molecule. What does it do? Speed of light photon comes in and speed of light photon goes out. So where's the thermal energy storage? Okay, if it's going to hold it for a long time, then it's really not doing anything with it, and then it can't take any more while it's holding it. And if it's going to pass it on, then it's momentary and it's not doing anything either. So no matter how you look at the CO2, it's kind of worthless.
It's a legit animation, right? It's a bit more fun than those equations, but the equations are valid.
It's just a stupid little thing. It's a molecule. So let's just say that it gets an infrared photon. Oh my gosh. And it spits it out again. Whoop-de-doo. It spits some of it to the space and some of it back to Earth and some to other molecules, and then it's gone.
The way that I, as a non-thinking person, when I'm hearing global greenhouse gas, it seems to me when they're talking about greenhouse gases is that the atmosphere is turning into an actual physical glass-like thing with the gas, where the gas changes state and it basically absorbs things and all that.
No, it's not like that at all. So, I mean, CO2 definitely matters if you're on Jupiter, okay, but not here on Earth. I mean, it does matter because it's the basis of all life on Earth. The C in CO2 is carbon. The carbon goes into plants. So the plants take the air and they get carbon from it. They don't get much carbon from the soil. They get it from the air. So without CO2 in the air, we wouldn't have any plants, basically. Without any plants, we wouldn't have any animals. Okay, so that's C. So CO2 is your friend. Okay, it's like I said, it's one of the. If there was a greatest hits of molecules, the CO2 would be on it. It's a good one. We're damn lucky to have that. And you have a place like Mars or Venus where you have 90+% CO2. Venus is hell, but it's close to the sun, and Mars is worse than Antarctica. Okay, it's got all the CO2. It's like 93% CO2 atmosphere. So it didn't warm Mars. Okay, so anyway, the CO2, it's a big fraud, and they again because industrial societies burn fuel, they produce CO2, and it warms the air. And and therefore industrial capitalism is a basis of industrial societies. Therefore, capitalism is evil because it warms the air. And CO2, so they vilified CO2 when it is actually the basis of all life on Earth, or one of the bases of life. And so it's just a political fraud. And they're using it. They want $25 trillion. That's the whatever the thing. I like to remember things that are bad. but the European they're trying to get $25 trillion out of this heist. Okay, it's basically what it is. Okay, so so that's sort of what I wanted to talk about today. I want to just keep it simple. I mean, these things look complicated, and they are. You don't. If you saw this on, if you're going through the internet one day and you saw this on as a picture, you go, huh? You don't really get it.
Yeah.
Okay. So, but if you do look at it, then you start to say, what is 7.6 millipascals? Well, you got to kind of know in the back of your mind that one atmosphere, because I put these things on there, one atmosphere is only 0.1. So that's 76 atmospheres or 75 atmospheres. So there's that spike. So then it starts to mean, you say, oh, so that's only relevant and for the vibration analysis of a greenhouse gas at 75 atmospheres. Well, we don't have that problem here, so it's not really relevant.
That's a pretty specific experiment by Xiaolai Zi and Pixai Yang, to sit down and make that.
Well, they're using it. But CO2 is an industrial gas, so they actually do. So there's a lot of data out there, and this is actually from the NIST web books. NIST is the National Institute of Science or whatever standards and something or other. Anyways, so that's a U.S. government. They just happen to be Chinese researchers, whatever, or maybe they're American researchers with Chinese name. It's probably. Anyways, this is where it comes from. This is. I think. Oh, I see. I think these Chinese researchers took it from the U.S. government site. Okay, so that's where the data comes from. Okay, so but here is your real on the right side is your real relevant data. Here's your Earth conditions. You see, this is 100 degrees Celsius, so that's boiling. So we don't live in a boiling atmosphere. Okay, we live down here, 20, 40, 60. I put the temperatures down here on the bottom. So here's our little band of relevancy. In CO2, the blue line has less. Has a lower specific heat. It stores less thermal energy on a given temperature than air does in general. So it ain't a greenhouse gas, folks. It's less of a greenhouse gas than air is. So that's the basic idea. Now, returning to real quickly to last week, I mentioned we had this really hot period up here in the Northwest, and but then these temperatures say so. So this dark red here, you can see these are anomalies. In Fahrenheit. Okay, so the anomaly is up in 20 degrees anomalies, higher than usual. But then over here is some blue. Okay, so this blue down here is 24 below the normal temperature. That's 20 above, and that's 20 below. So so you basically have some extremes on both sides. Now here's this is the United States, and here's the whole globe at the same period of time. Okay, so here's the Northwest, and here, look over here in Argentina, we got a lot of blue down here. Then down here, we got some real hot and Antarctic weather, and then we've got some real cold period or place above that latitude.
So basically, everything's averaged out in this diagram. What you're saying?
Yeah. I mean, the white is where it's the same, zero anomaly, and this is anomalies again in Celsius, and so but. Yeah, some blues and some reds, and some white. And so you basically have it sort of, so can you say because there's a spot of red over here that the Earth is boiling and that we're all going to die? It's a bit of a stretch there, I wouldn't go screaming off of a cliff right now. I would encourage you to keep your cool and just not think that the world was boiling and the seas, turning into acid. Okay, so anyhow, so that's sort of the thing. And then there's one other thing I want to show. This again has to do with lit in Canada, which we talked about. This was interesting to me. Remember, up in the higher latitudes, they have the land of the midnight sun sort of thing going on, right? So in the middle of the summer in July, they have 11 and a half hours of sunshine every day. So they got a really high temperature. Well, we don't get 11 half. I'm in Florida right now. We don't have 11 and a half hours of sunshine. Okay, so that's a lot of sunshine. So the temperature went up higher. So it's interesting. And then here's an explanation by AccuWeather meteorologists, and it basically just says that this is why they had this. then I had somebody. I could go through all that, but if we want to look, I'll just leave the screen up for a few moments while I explain. But there's one guy up from Portland. He says, Kevin, we know that there's in a few times since the 1960s, since we've been around, that we get these hot spells in Portland and around. And we don't. They do get very hot. He says everybody knows it. He says the only difference between the hot spells now and the ones before is the degree of hype. Okay, so
Yeah.
So that's what it is. It's just and why the hype? I tend to think that when I and others start to challenge, I think my work is a little bit heavier because I've attacked I've exposed the theory itself as invalid, where a lot of other people are still trying to it's quantify this. They're looking at the CO₂. They're conceding the greenhouse gas theory. They haven't challenged it generally, and they'll see the CO₂ as just a small part. And then they this or that or the other thing, but not many people challenging the greenhouse gas theory itself. And but I challenge it directly because I had, like I said, I had some intellectual tools in my toolkit that gave me an advantage. But nonetheless, I think we're going to see the academics and the so-called scientists scrambling now and going and exaggerating even more because they're exposed. And so we need to take advantage of this exposure of the academics. We need to restore one of my longstanding concepts that I've advocated is that education in the future will be software driven. We can have so much more responsive and pedagogically advanced software technology for learning that we are not going to need to be so dependent on the massive expenditures of government towards education / indoctrination. I think that's probably the wrong word. It should be indoctrination / education. And just like I say, when we as people can't handle this, even after 16 years of education, if we've gone to college, this is straightforward. All we're saying is, what does the temperature depend upon? This is the ideal gas law, PV equals nRT. Temperature is only dependent upon the velocity of the molecules, not their vibrations or their molecular structure or whatever. It doesn't have anything to do with molecular structure. And you can see that, bam. So, but we should have better grasp of these fundamentals than we do. And the fact that we don't is sort of a failing of our educational institutions in our society.
Yeah, when I look back to my
like I said,
when I look back to my primary school, I pretty much all I can really remember is English lessons that I found quite boring, and then these repeating maths calculations like multiplications by 8 and 9 and adding like 10 to, and just over and over and over again. Like, that's just not how you would learn this stuff nowadays,
Yeah, no, this is important. This is relevant. Kinetic theory is a mainstream science. This kinetic theory shows, and I've got more work that we can discuss in a future time if you want. And I think we should.
Sure, mate.
But more work advancing the science of climate science, which is really important science for a lot of people. And we need to restore credibility and legitimacy to this science, because it's just way out of kilter. And so we're basically going to the basics. And I've done that. This is like one of 9 subjects, this kinetic theory analysis that I've done in my paper. So it's only one of 9. This is the first one I wanted to, but it's something everyone can understand because they've all dealt with it. They don't think about it all the time, but they've seen it. And PV equals nRT. And this is the ideal gas law, but it basically is showing that the temperature is dependent upon the mass of the gas and the velocity, the average velocity of the molecules, not their molecular structure. Okay, not the CO₂ and the methane. It has nothing to do with the temperature. Okay, and then when we go again, temperature, the air. It's all about thermal energy storage. How much thermal energy can the air store? If you alter the concentration by increasing the CO₂, At a constant pressure, it can store less thermal energy, which means CO2 is an anti-greenhouse gas. Okay, add more of it, the air can store less thermal energy. Now, it might heat up faster because it takes less energy to heat it, but the actual thermal energy storage there is less. It could melt less ice at a given temperature because it has less thermal energy in it. So CO2 is an anti-greenhouse gas, not a greenhouse gas. And I've explained before, CO2 is the basis of photosynthesis, which is an endothermic reaction which takes thermal energy and converts it into carbon life. So CO2, no matter how you cut it, is an anti greenhouse gas if there was such a thing.
I just read an interesting quote here on Twitter by Charles Gasparino when we're talking about like people's agenda and maybe we are the serfs that have to pay our carbon tax. He says little insight into the absurdity of at Bill Gates giving a climate speech today here in #Sun Valley. The local airport had to delay flights because the place is so jam-packed with those carbon-emitting Gulf Streams owned by the billionaires who attended this thing. You know.
Yeah. Well, the way that I see to challenge these bozos going around enslaving us by stripping us of our fuel use is the science and good science. I mean, I'm happy to discuss any aspect of what I discussed today with others in public. It's a running challenge. Happy to. That's hey, if you show me that I'm wrong, I'll have learned something. I welcome you. Thank you for explaining something, But if you're going to challenge some of these, I mean, people say, well, this should be CV rather than CP, constant volume. And I say, no, constant pressure because so we'll discuss it. Okay, I'm happy to open the topic, but if you can't counteract it and find errors in the reasoning or the premises or show them invalid, then you've got to concede that maybe I'm right and don't be so jealous of me or something like silly like that. That's not what it is. It's about science. Science is like, these are ideas. It doesn't, once I've expressed them, then they're ideas and it's knowledge. And if you want to beat it to death and it no longer stands, then it's no longer knowledge. But if it's knowledge because it stands, then we want to make decisions based upon sound knowledge, not invalid knowledge. And the greenhouse gas theory is invalid. And we don't want to make any decisions based upon an invalid theory. So, spread this around to show people that, and I try to bring it back down to the world that most people come from, and so that they can relate to it, because they should be able to. Like you said, if you've got 12 to 16 years of education, that is a lot of years. Okay, so you've got it. So
what did
go
you
back
actually learn in that 10 or 12 years? What did we actually?
Yeah, I know. It's a question. It's got to be a running.
When I first went to university. So, anyways, when I first went to university, I was in first year doing mathematics, and I had a friend from Pakistan. I think he was called Kamran or something like that. I can't remember now, but he was basically going to the math lecturers and he's saying, "Why am I family paying £12,000 for this? I knew all this in high school. This is ridiculously easy, And I was embarrassed,
Exactly.
By my economy.
Yeah, that's yeah. It's too many. Like I say, we can't change the world. People are going to think whatever the heck they want, but we should be thinking capably as individuals for ourselves. And the more we do this, the better off everyone is, the more stable the world becomes. So, if you're an intelligent, honest person out there, study a little science and be confident enough to challenge invalid ideas and poor reasoning, and so that we're not making collective bad decisions, because bad decisions, they can screw us all. No, we're just a planet of a species. There's 8 million of them, but we're one of them. And if we are wiped out tomorrow, like the Neanderthals, the rest of the universe won't really give a crap. So we better care. And so we have to. So again, new science is good. I worked at this for 10, 11, 12 years, so I should be it should be attributed to me. I'm not, I don't gain a whole lot. This is, this is notorious science, at this present time, but it should be recognized, and it should be integrated in with the mainstream, not isolated. And again, I'm trying to return to mainstream information. This is NIST data, okay, about the nature of and this explains what goes on with the CO₂ molecule. It only occurs under 76 in huge pressures. And normal pressures, hey, CO₂ is not a greenhouse gas; it's the opposite. Okay, so these are important things. And again, if you want to challenge them, tell Nikos or write me, and let's get you on here, and let's have a
it's getting, no disrespect, but it's getting boring just having like the winning team all the time. It's like winning a computer game and there's no competition. You just like get bored. You want some competition,
Yeah.
Like,
well, that's right. But if in the absence of competition, it means I'm still king of the hill. And if I'm king of the hill, then what needs to be done is more people need to be recognized, because then they'll start to be embarrassed when they start saying, about global, sort of warming-ish sort of thing. And then if they're standing up in front of a group of 500 people, they start talking about CO₂, and they hear some boo, go sit down, and then they'll go, well, CO₂ and air and argon, all those things are important. and they won't say anything anymore, and they'll stop using it as an excuse to screw everyone over.
But the thing is, that in a sense is a fantasy scenario, because like we look at the media and it is just insane. Like the EU are now talking about this sort of like green taxis and just it's
scary.
It's scary.
It's like march the minority into the camps and put them into gas chambers. It's like, my God. I mean, that's fundamentally, it's what they're advocating, except it's more complicated. So you can't say it like that.
I read a post the other day where it was, I haven't had time to fact check it, but it's saying like within 10 years, only 3 airports in the UK will be open, and we're planning to shut down them or something like that.
Yeah. And so what are they gonna? How are they? So they're gonna type money into computer, and then people are gonna eat, right?
Yeah.
That doesn't follow. So I don't know where they're getting that reasoning from. They type numbers into a computer and then everyone eats. That doesn't follow. I'm sorry.
I think what the conspiracy theorists, and I'll use that in quotes, are saying that basically the powers that be want to keep people separated internationally so they can do what they want in the country.
Yeah.
So some people traveling, then that's
I don't know. I mean, if the whole world were like North Korea, I think the guys at the top would have their heads severed. So I don't think their plan as the so-called elite is very well thought through. So I think their days are numbered, to use an old expression. But anyways, let's focus on what we can do, which is to see valid knowledge prevail and challenge invalid ideas, and do so in a respectful way, but understand the nature of the forces that oppose valid knowledge and that oppose advance of scientific understanding. So we have to fight. We have to fight with passionately and capably against the enemies of enlightenment and the enemies of science. And that, I hope we can wrap this up, because I can't go on this forever.
Well, yeah, thanks very much, Kevin. I really you're an important person in the world right now, because you have this sort of unique background where you had worked in industry, you're trained in mechanics, and you understand the science, and you're also willing to put yourself out there and be ridiculed by all this climate change fan club.
I was reading some Stoic philosophers, and they said something recently. I'm not a Stoic per se, but they said basically, if you have knowledge and it's an advance, it's kind of worthless to yourself if you keep it to yourself. So so in the one sense, you need to if you're going to contribute to human evolution, then it's kind of interesting because everybody's excited there. It's new. It's something important, and that's neat. But if you just keep it to yourself, then it's really not doesn't really, it's kind of boring. So it needs to be brought out. And so I've done a lot of work on this, and people need to start talking about it, and they need to grow in their self-confidence to think capably themselves. So anyways, okay, great. Nikos, thanks again for having me. So.
Okay, thanks Kevin, and we'll have you on again. And thanks for my listener for joining us if you've made it this far. This is actually a really practical podcast today to give you tools to go make your own decisions and research, and to be objective when you are watching this. So from me and Kevin, this is the Nikos Show today. See you later. Bye-bye.